So we've been studying the spring mass system, and we've looked at free motion. Okay, we looked at free undamped and free damped motion. And now we'll turn our attention to driven or forced motion. Okay, so now we're going to get non-homogeneous equations. We get this external force acting on the spring mass system, and looking at Newton's second law, mass times acceleration is the sum of the forces. Here's our spring force, here's our damping force, and here's this external force being applied. Rearranging, moving these two terms to the other side, and then dividing by m, we get this differential equation here, where you see these relations. And let's take a look at an example. So interpret and solve the initial value problem that we see here. So this differential equation can be interpreted as a spring mass system because it respects this form, with the mass equal to 1/5. Okay, again, we're just looking at what you would get from moving this to the other side. So the mass that's in front of the d squared x dt squared term is 1/5. This is 1.2. Again, this is positive there because you're moving it to the other side. So beta is 1.2. And this negative kx, move it to the other side. And you could get a k equal to 2. Okay? And we're left with this term here, which is the driving force. Okay? So that's the external force that's being applied. The system begins at t equals, we consider the system starting at t equals 0 because that's where our initial conditions are. And positive 1/2 corresponds to below the equilibrium position, with the initial velocity of 0 at rest. Okay, so the system starts at rest, 1/2 unit measure of length below the equilibrium position. So we could rewrite this by multiplying by 5, and we get that differential equation. The associated homogeneous equation is what we see here, giving these two roots to the auxiliary equation, and so we get a complementary function that we see here. For a particular solution, let's use the method of undetermined coefficients, and we're going to assume this form here. There is no duplicated term from the complementary function, and so this is coming from the problem. This is coming from plugging in our assumed form, and we match coefficients to get these two equations or this solution there. And so our general solution is the complementary function plus the particular solution, and we get what you see here. How do you fix C1 and C2? You apply the initial condition. So 1/2 at the initial position is the initial position at t equals 0, and so we plug in 0 into what? Into our general. So the whole, general solution there, and this gives us C1 is equal to 338/51. And if we do the same thing, but of course you got to take the derivative. Okay, I don't write it here just because, product rule, and it's going to be a longer expression. But if you take the derivative and then plug 0 into what you find for an expression of the derivative, plug in 0 and then set that equal to 0, you get that C2 is equal to this. And so fixing these constants, plugging in these constants into our general solution, we get what you see here. Now, something to pay attention to here is notice that this term here, as t goes to infinity, this grows. This term e to the 3t will grow exponentially large, which means e to the minus 3t grows exponentially smaller, right? It goes down to 0 fairly quickly in an exponential manner. Okay, and this term here is just oscillatory, right? Cosine has a max of 1, sine has a max of 1, and min of minus 1, right? And so this term here goes to 0 as t goes to infinity. Okay. Terms that go to 0 as the time goes on are called transient terms in general. And here, the complementary function is a transient term, or transient solution, it's called. Now, the part that persists as t goes to infinity is called the steady state term or solution. And so this term goes to 0, it's a transient term, but this remains. And so here is our steady state term or solution. So let's look at another example. We want to solve the initial value problem. So here we are using symbols more, except for the initial conditions. We have at time equals 0, you start from equilibrium position, and you start with 0 speed. And now someone might think that's boring, right? Nothing's going to happen, but don't forget that there's a driving force here. Okay, so it'll drive the system despite starting from equilibrium position and at rest. Okay. We're going to assume that omega is not equal to gamma, which is the frequency of the driving term, the driving force. Well, doing what we've done plenty of times at this point, getting the associated homogeneous equation, getting the complementary function. Here goes your complementary function. For a particular solution, we're going to use the method of undetermined coefficients, and we're going to assume this form. Now, because we assumed omega is not equal to gamma, there is no duplication. Okay. If we do consider the situation where omega could equal gamma, then we'd have to multiply this by t to avoid duplications. Okay. But we've assumed that omega is not equal to gamma, so we could just straightforwardly, here's from our problem, here's from plugging the particular solution. Matching coefficients, we get a equals 0, b is equal to this. And so here goes our particular solution. And here goes our general solution. Let's apply the initial conditions and get these constants, and we are left with this solution to this IVP. Okay? Again, you treat these, despite them being letters, you treat gamma, omega as just parameters, constants. Now, if we dealt with the situation where actually omega is equal to gamma, we could do this problem all over again, and this time get rid of the duplication by multiplying by t. Alternatively, we could do something else to get that solution, actually. We could get that solution from this form. Okay, how do we do that? Well, we could just compute the limit as gamma goes to omega of what we found here in this solution. So let's do that, okay? We're going to call this x resonance to distinguish from this previous x that we solved, okay? And of course the problem here is that you get 0 in the denominator, and you get also 0 in the numerator. How do you deal with that problem? You use L'Hopital's rule. So you take, and because we're the variable that we're, yes, it is a parameter, but here we're varying it in the limit, so we treat it as a variable. So we take the derivative with respect to the variable that we're varying, which is gamma here, and so we'll take the derivative of the top and bottom, and we then get this, and now we don't have the problem of the indeterminate form, and we're left with this, which we could write this way. Okay? And now look at this term here. This term grows linearly with t. Okay, as time goes on, this just keeps getting bigger and bigger. Okay, this is telling you that the amplitudes are getting larger and larger. Okay, the absolute value of this goes to infinity as t goes to infinity. Okay, that phenomenon is called pure resonance. Okay, we don't even have a damping term here. And in general, resonance occurs when a system is driven at the natural frequency. What is the natural frequency? It's omega. It's omega, which is equal to k over m. okay? The spring constant over m, so the square root of that is omega. And that's the sort of natural frequency of the spring. That's the frequency that the spring feels comfortable being driven at. For example, if someone is swinging on a swing, you know, you don't push them while they're going down and pull them while they're getting farther. You push and pull according to the frequency that's conducive to motion of the swing. That's the sort of natural frequency of that spring. And so what happens when you're pushing a system, the spring mass system, that doesn't have damping at this natural frequency is that you're getting amplitudes that are growing ever larger, okay? So you could think about this T term, you know, as an envelope where instead of having exponential damping for a underdamped system, right? Here you're actually getting this envelope that's growing as T, and you're getting this kind of growing. Okay, now what would happen in a real system is eventually the spring will just break, or you'll have maybe a spring that would not obey Hooke's law anymore because you've taken it to such an extreme. And note here that we haven't considered damping. Damping could sort of mitigate this pure resonance effect, okay? It could mitigate this growth there, okay? So in general, when you're driving a system at its natural frequency, you get resonance, as we've seen here.